This episode is all about three related abstract data types: stacks, queues, and priority queues. Since they're abstract, you can implement them in various ways. In the episode after this one, we're going to talk about how you could implement a priority queue with a data structure called a heap. So along with arrays, I'd say stacks and queues are the foundation for everything else. Stacks and queues are very similar in that they both let you add data to them and they let you get data back out in some prescribed order. The canonical example of a stack is a stack of plates. You push a new plate onto the stack, and when you need a plate, you pop it off the stack. This means that a stack has a last in, first out semantics, and this is often abbreviated LIFO. And I don't know why it isn't first in, last out, FILO, because that would be more fun. The point here is that the most recent thing that was added to the stack will be the thing that you get back if you ask for data. The data that was pushed onto the stack first is at the bottom of the stack, so it's going to be the last thing that you get back. Really, just visualize a stack of plates and you can remember how this works. Stacks have a lot of applications. A programming language compiler or interpreter, for example, uses stacks to parse your source files. If you've done any graphics program, you might have used stacks without even realizing it. You can push push state onto a stack, modify some settings and use them, and then pop the stack to restore the state that you had earlier. Stacks also have special words to go with them. When you add data to a stack, you push onto the stack. And when you remove data, you pop the stack. And if you want to read but not remove the data from the stack, you peek the stack. Queues are in some sense the opposite of a stack. Queues are first in, first out. Imagine we're all English and we're forming queues when we're waiting around for something. The first person in line is the first person to leave the line, and that's fair, right? So remember this phrase, FIFO, first in, first out, and you're going to see that everywhere. A bare bones queue doesn't need to give you operations like random access by key or index. It doesn't even need to give you the size. All a queue is required to do is remember which order things were put in so that you can remove them in that order. There are special words for adding and removing from queues too. I don't know why. NQ is the fancy word for adding to a queue. DQ is the fancy word for removing from a queue. I've also heard people use push and pop to mean NQ and DQ, though usually those are stack words. So stacks and queues are linear, meaning that they record an ordering based on what items showed up when. Despite that linearness, they're very useful in traversing nonlinear structures like graphs or this tree here. For example, when you walk a binary tree, there's a record of the order that you encountered nodes, which has stack semantics. Graph algorithms also use queues and stacks all the time to keep track of which order to process data. So now we're going to get to priority queues, which are like normal queues, but you can prioritize the data that they contain in some way. In this drawing, the queue prioritizes people by height, shortest first, and obviously this is ridiculous. A more realistic example might be when people wait their turn at the emergency room. People with some traumatic situation will be prioritized ahead of people with, paper cuts. So a priority queue is often used to arrange activities so that we always handle the most important one next. So at the emergency room at the hospital, we rightly want to prioritize serving people with life-threatening medical situations over those who are merely in agony, and again, prioritize those in agony over those who can, probably wait a few hours. When you add something to the priority queue, you use its priority to put it in the right place. In this situation, people's situations have a priority number. So if somebody comes in with priority 7, for example, they're going to be placed between the people in this drawing between priority 5 and 8. I really need to talk with my production staff about these pictures. I'm sorry. So if you add a low priority thing to a priority queue, it will end up at the back or near the back of the line. But adding a high priority thing will place it towards the front. The highest priority thing will always be the first in line. Second highest is next, and so on. A priority queue is an abstract data type. You could implement it in any way. You could keep a list or a sorted array or use magical elves, as long as you can enqueue things with priorities and dequeue those things and get them back in the priority queue, priority order, you have a priority queue. So what are some ways of implementing a priority queue abstract data type? There's loads of ways to do this. And remember, you have to obey the abstraction. Enqueue to add items with a given priority, dequeue to remove and return items with the highest priority, and peek to see what the highest priority is without removing it. And that's all the ADT is. One way that we could do this, which is not efficient, but it's easy to understand, is to just hold all the items along with our priority in an unsorted list. When we enqueue something, we put it in the list wherever, and that's constant time complexity. When we peek or dequeue, we scan the entire list to find the one that has the highest priority. In that case, we're also talking linear time complexity because we have to look at every item in the queue to figure out which one has the highest priority. So we can do better than that, for sure. In the next episode, we're going to talk about something called the binary heap, which is a concrete data structure that is often used to implement the priority queue abstraction.